Curvilinear coordinate systems 9. Use the differential operator theorems to evaluate a closed surface integral d sigma dot b using spherical coordinates, where S is the surface of a sphere of radius capital R centered at the origin, and V is in part A x Ex hat plus y Ey hat plus z Ez hat. Now this is basically talking about the flux of this vector V. Therefore, we're going to use Gauss theorem. Gauss theorem tells us that the volume integral d tau divergence of the vector V is equal to the closed surface integral d sigma dot product with vector V. Now this is known as Gauss theorem. All right, so let's use Gauss theorem and evaluate this integral. In part A, we are given the vector V x Ex hat y Ey hat plus z Ez hat. So we need to take its divergence. Divergence of vector V is del x plus del y. That's basically the position vector divergence we're taking. Y plus del z. Therefore, we're going to get x derivative 1, y derivative 1, z derivative 1, 1 plus 1 plus 1. Divergence of V is equal to 3. Now, the differential volume element in spherical coordinates is r d theta, r sine theta d phi, multiplied with dr. So these are the two arc lengths, one on the when we vary the polar angle, one when we vary the azimuthal angle, and this is where I change the radius. So this gives us the volume, differential volume, r square sine theta, which is also the product of the scale factors hr, h theta, h phi, dr d theta d phi. Okay, now we're ready to perform the volume integral d tau divergence of V. Divergence of V gave us a factor of 3. Our volume element r square sine theta dr d theta d phi. It's a triple integral. Dr d theta d phi. So this is going to be performed over this sphere of radius r centered at the origin. Therefore, our r varies between 0 and capital R. So we have r square dr. The angle theta, the phi varies between 0 and 2 pi. So we have d phi. And the angle theta varies between 0 and pi, which is going to give us, so there's a factor 3 here, sine theta d theta. Now performing these integrals, we obtain from the r integral, capital R cube over 3, but there's a 3 here, so it will be just capital R cube. The phi integral will give us a factor of 2 pi, phi evaluated between 0 and 2 pi. The integral of sine theta d theta is minus cosine theta evaluated between 0 and pi. Cosine pi is -1, cosine 0 is 1, so minus 1 becomes +1, +1 minus -1 is going to give us a factor of 2. Therefore, this will be 4 pi capital R cube. So, according to Gauss theorem, we have the surface integral, closed surface integral, d sigma dot v must be equal to 4 pi R cube. Okay. So we have used Gauss theorem to evaluate the surface integral d sigma dot v, and v is our vector, position vector, which has a divergence of 3 using divergence in Cartesian coordinates. Then we evaluate the integral in spherical coordinates. So our d tau, the volume element, is r squared sine theta dr d phi, which is the product of the scale factors hr, h theta, h phi, multiplied by the differential changes in the curvilinear coordinates, and the volume integral d tau divergence of v, since divergence is 3, gives us integral from 0 to capital R, r squared dr, integral from 0 to 2 pi d phi, integral from 0 to pi sine theta d theta. To cover the full sphere here, we have to vary the polar angle from theta to pi, and then we have this slice here, and 0 to capital R basically gives us this slice, and this slice has to go over all possible phi values between 0 and 2 pi to cover the full sphere. So that's basically what I have done. The r squared dr integral gives us capital R cube over 3. 3's cancel. We have capital R cube. Pi integral gives us 2 pi. Sine theta d theta integral is minus cosine theta evaluated between 0 and pi. And this gives us our final answer for the closed surface d sigma dot v integral, 4 pi r cube.